The morning of February 22, 1944, 27,000 feet above Oschersleben, Germany, Captain Lester Rentmeester sat in the left seat of his B-17 flying fortress, Jeannie Marie, watching tracer rounds arc past his windscreen like strings of Christmas lights trying to kill him. His throttles were pushed to the firewall. His manifold pressure gauges read 62 inches of mercury. His 4 Wright Cyclone engines were generating 4,800 horsepower combined, and it wasn't going to be enough. The Messerschmitt Bf 109 that had just put 20mm cannon shells through his No. 2 engine was coming around for another pass. Rentmeester could see black smoke streaming from the inboard port engine. Oil pressure was dropping. Cylinder head temperature was climbing into the red. The propeller was windmilling, acting as a massive air brake, pulling the bomber into a lazy left turn that required constant right rudder to overcome. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Behind him, 9 men watched their aircraft take damage that should have killed them all 3 minutes ago. But the B-17 flying fortress had earned its reputation the hard way by bringing crews home when every law of physics and aerodynamics said the aircraft should have disintegrated. Today, Jeannie Marie was about to earn her place in that legacy. Today, Rentmeester and his crew were going to learn exactly how far a crippled bomber could fly on hope, skill, and the fundamental aerodynamic principle that every pilot learned but few ever had to trust with their lives. A powered aircraft could extend its glide range far beyond what seemed possible if the pilot understood the relationship between altitude, distance, and the agonizing mathematics of trading one for the other. The United States Army Air Forces had been conducting strategic bombing campaigns against Germany since August of 1942. The theory was elegant. Destroy Germany's industrial capacity to wage war by hitting factories, refineries, and transportation infrastructure with precision daylight bombing. The reality was considerably messier. German fighter pilots and anti-aircraft gunners had spent 2 years learning how to kill American bombers with ruthless efficiency. By February of 1944, the 8th Air Force had lost over 2,000 B-17 seconds to enemy action. That number represented roughly 20,000 aircrew members dead, missing, or captured. The statistical reality facing every bomber crew was brutally simple. A 10-man crew had to survive 25 missions to complete their combat tour. Unit records showed that crew members had approximately a 25% chance of surviving those 25 missions. 3 out of every 4 men who climbed into a B-17 would eventually be killed, wounded, or captured. Captain Rentmeester understood these statistics intimately. This was his 23rd mission. He had watched other aircraft explode mid-flight when cannon shells found bomb bays still loaded with ordnance. He had seen B-17 seconds break apart under sustained fighter attacks, pieces of wing and fuselage tumbling through the formation while parachutes bloomed like tragic flowers against the winter sky. He had flown home with dead crew members in the tail section and blood frozen to the interior bulkheads at 60 degrees below 0 Fahrenheit. The target for today's mission was the AGO Flugzeugwerke aircraft assembly plant in Oschersleben, approximately 100 miles southwest of Berlin. The plant produced Focke-Wulf 190 fighters, and 8th Air Force intelligence estimated it contributed roughly 12% of Germany's single-engine fighter production capacity. Destroying it would temporarily reduce the number of fighters that could intercept future bombing raids. 124 B-17 seconds had launched from bases across eastern England before dawn. Rentmeester's 91st Bombardment Group contributed 20 aircraft as part of the massive formation. The bomber stream stretched for miles, stacked at varying altitudes to prevent mid-air collisions while maintaining defensive formation integrity. Each B-17 carried approximately 4,000 pounds of high-explosive bombs. Total payload for the mission exceeded 1 million pounds of ordnance. The flight plan called for the bombers to cross the English Channel, transit across Belgium and the Netherlands, enter German airspace near Brunswick, then proceed to Oschersleben. Total distance from base to target, approximately 500 miles. The return trip would follow a similar route, weather permitting. Total mission duration, approximately 8 hours, including time over target and the bombing run itself. German defences were formidable. The Luftwaffe maintained approximately 1,500 operational fighters across various bases in northern Germany. Fighter Command Headquarters at Diemen in the Netherlands coordinated intercept operations using an extensive radar network that could track incoming bomber formations from over 100 miles away. Ground controllers vectored fighter units to intercept points calculated to maximize effectiveness while conserving fuel. Rentmeester's bomber, Jeannie Marie, had crossed the English Channel without incident at 10:41 hours. The weather was typical for northern Europe in late winter. Broken cloud cover at lower altitudes, clear skies above 20,000 feet, outside air temperature -60 degrees Fahrenheit. The crew tested their oxygen systems and weapons during the channel crossing. All systems functioned normally. German fighters first appeared at 11:15 hours, approximately 30 miles northeast of Magdeburg. Rentmeester spotted them through breaks in the lower cloud deck, black specks climbing, from below, resolving into the distinctive silhouettes of Bf 109s and Focke-Wulf 190s. Radio chatter immediately increased as other pilots called out fighter positions using clock references and altitude estimates. Bandits, 12 o'clock level, coming in fast. I count 15. No, 20 fighters forming up at 2 o'clock high. Here they come. 6 Focke-Wulf 190s dove from 29,000 feet, rolling inverted and pulling through into near vertical dives that brought them screaming through the bomber formation at closure rates exceeding 500 miles per hour. Their 4 20mm cannons and 2 13mm machine guns poured fire into the lead elements of the 91st Bombardment Group. Rentmeester watched a B-17 200 yards ahead take a direct hit. The bomber simply disintegrated, transforming from an aircraft into an expanding cloud of aluminum, fragments, fuel vapor, and unrecognizable pieces of what had been 10 human beings seconds earlier. No parachutes emerged from the fireball. The second attack wave came from head-on at 11:23 hours. German pilots had learned that frontal attacks presented the smallest target profile and encountered the least defensive firepower. Early B-17 models had limited forward-firing armament. Even the improved B-17G model with its chin turret couldn't generate sufficient fire density to deter determined attackers willing to press their runs to point-blank range. 3 Messerschmitt Bf 109s bored straight into the formation from 12 o'clock level. Rentmeester could see muzzle flashes winking from their nose-mounted cannons and machine guns. Tracer rounds drew lines of fire through the formation like deadly geometry. His top turret gunner, Sergeant Elmer Diathorn, opened fire with his twin 50 caliber machine guns, sending tracers arcing toward the attacking fighters. Then the impacts began. The first cannon shell hit Jeannie Marie's No. 2 engine, cowling with a sound like someone hitting a bell with a sledgehammer. Metal fragments peppered the left side of the cockpit. The engine instruments for No. 2 immediately showed catastrophic failure, oil pressure dropping to 0, cylinder head temperature spiking above red line limits, manifold pressure collapsing. Rentmeester's co-pilot, Lieutenant Bill Behrend, reached for the No. 2 engine controls without being told. He pulled the throttle back to idle, then hit the feathering button to rotate the propeller blades edge-on to the relative wind. This would stop the windmilling and reduce drag. But the feathering motor wasn't working. Electrical damage or hydraulic failure or battle damage to the feathering mechanism itself. Whatever the cause, the propeller continued windmilling at high RPM, acting as a massive air brake. The second cannon shell struck moments later, hitting the No. 3 engine nacelle, with enough force to shake the entire aircraft. This hit was less severe, but Rentmeester immediately noticed No. 3 engine performance degrading. Power output dropped from full war emergency ratings to roughly 50%. The engine would continue running, but it wasn't going to provide meaningful thrust. Jeannie Marie now had effectively 1.5 engines providing thrust, the outboard No. 1 and No. 4 engines at full power, and No. 3 limping along at half power. No. 2 was dead, its windmilling propeller generating enormous drag. The laws of physics were unforgiving. 4,800 horsepower had just become approximately 3,200 horsepower, And that wasn't enough to maintain altitude with a 10-ton aircraft carrying combat damage that increased drag beyond normal parameters. Rentmeester made his decision in approximately 3 seconds. Turning back toward England meant abandoning the bombing run. But staying with the formation on reduced power was impossible. The bomber was already falling behind, losing both airspeed and altitude. Stragglers attracted German fighters the way blood in the water attracted sharks. A lone, crippled bomber separated from formation firepower was essentially defenseless. "Navigator, give me a heading direct to the Belgian coast," Rentmeester called over the intercom. "We're going home." Lieutenant Bob Roberts, the navigator, was already pulling out his charts. "Copy that. Heading 270 degrees magnetic will take us direct to the coast. Distance approximately 350 miles. 350 miles. Rentmeester looked at his altimeter. 24,500 feet. He did the mathematics in his head, calculations every pilot knew but hoped never to use. A B-17 without power had a glide ratio of approximately 16:1. For every 1 foot of altitude lost, the aircraft travelled 16 feet horizontally. 24,000 feet of altitude equaled roughly 4.5 miles vertical. Multiply by 16, approximately 72 miles of glide range with 0 power. But Rentmeester still had power from 3 engines. Not much, but enough to extend the glide significantly. If he could maintain a shallow descent while extracting maximum efficiency from his remaining engines, trading altitude for distance at the optimal rate, he might make it back to friendly territory before running out of both altitude and options. The problem was German fighters and German anti-aircraft guns, and the simple mechanical reality that engines damaged in combat had a nasty tendency to fail completely at the worst possible moment. And the fact that his current descent rate, even with partial power, suggested he'd reach ground level somewhere over western Germany, approximately 100 miles short of the Belgian coast. Every foot of altitude was precious now. Every minute of engine operation was a gift. Rentmeester eased the throttles forward on engines 1, 3, and 4, pushing through the detents into war emergency power. This setting provided maximum thrust by increasing manifold pressure and engine RPM beyond normal operational limits. Engine manufacturers warned that war emergency power caused accelerated wear and risked mechanical failure. Standard procedure limited its use to 5 minutes maximum. Rentmeester knew he'd be using war emergency power for the next 2 hours. Either the engines would hold together, or they wouldn't. Either way, he wasn't reducing throttle settings until the English Channel appeared below his wings, or the bomber hit the ground trying to reach it. The manifold pressure gauges for engines 1 and 4 read 51 inches of mercury. The tachometers showed 2250 RPM. Each engine was generating approximately 1500 horsepower, 50% more than normal combat power ratings. Cylinder head temperatures climbed, toward red line limits. Oil temperatures rose. The engines were being destroyed incrementally with every minute of operation, trading their mechanical lifespan for thrust that might keep the aircraft airborne long enough to matter. Engine number 3, already damaged, was barely contributing. Rentmeester could feel the asymmetric thrust trying to yaw the aircraft left. He pressed right rudder, using the bomber's vertical stabilizer to counteract the tendency. His right leg muscles burned with sustained pressure against the rudder pedal. His co-pilot helped, applying pressure to his own rudder pedals, sharing the physical burden of keeping the aircraft pointed in something resembling the correct direction. The aircraft was shaking violently. The windmilling propeller on the dead number 2 engine generated tremendous vibration that transmitted throughout the entire airframe. Rentmeester found he couldn't read his instruments accurately. The needles danced and blurred. He flew by feel, by instinct, by the seat of his pants, that ancient pilot's expression that meant trusting vestibular sensations and kinesthetic feedback over unreliable visual information. "Bombardier, pilot," Rentmeester called over the intercom. "Pull the green apple. Get rid of the bombs." Lieutenant Joe Ashby acknowledged immediately. The green apple was the emergency bomb release. a green-painted knob on the cockpit floor that triggered explosive bolts to release all bomb shackles simultaneously. The bombs would tumble away without their fuses being armed. They'd crater some German farmland or forest, doing no military damage, but eliminating 10,000 pounds of weight that Jeannie Marie could no longer afford to carry. Rentmeester heard the mechanical clunk of bomb shackles releasing. The aircraft lurched upward slightly as 10,000 pounds dropped away. Rate of descent decreased marginally. Every little bit helped. Every pound of weight eliminated meant slightly less drag, slightly better glide performance, slightly more distance extracted from diminishing altitude. They were passing through 22,000 feet now, still descending at approximately 300 feet per minute, despite full power on the remaining engines. The mathematics remained brutal. 300 feet per minute translated to 3,000 feet every 10 minutes. At this rate, Rentmeester had roughly 70 minutes before reaching ground level. Distance covered in 70 minutes at current ground speed, approximately 200 miles, still over 150 miles short of the Belgian coast. Unless he found a way to reduce descent rate, unless the engines kept running, unless German fighters didn't find them, unless a dozen other variables broke in his favour instead of against him. Rentmeester had been flying for 7 years, accumulating over 2,000 hours. He'd flown every B-17 variant from the early B-17C through the current B-17G model. He understood the aircraft's performance envelope intimately. He knew its limitations and its surprising capabilities. And he knew something that most pilots learned from training manuals, but few ever experienced viscerally: the relationship between drag, thrust, weight, and the curious aerodynamic phenomenon that allowed a skilled pilot to stretch a glide beyond what mathematical calculations suggested possible. The principle was simple in theory, devastatingly difficult in practice. Every aircraft had an optimal glide speed, the airspeed that maximized distance traveled per unit of altitude lost. Fly too slow and induced drag increased, steepening the glide angle. Fly too fast and parasitic drag dominated, again steepening the glide angle. Somewhere between those extremes existed a sweet spot where drag minimized and glide performance maximized. For a B-17 Flying Fortress, optimal glide speed was approximately 140 miles per hour indicated airspeed. This speed varied slightly based on aircraft weight, configuration, and atmospheric conditions. But 140 was the baseline that aerodynamic engineers had calculated and test pilots had verified. Rentmeester was currently flying at 180 miles per hour indicated, too fast. The excess speed was costing him glide performance. But reducing speed meant accepting less control authority, less ability to respond to emergency situations, less margin between current airspeed and the stall speed that would drop the bomber out of the sky like a brick. He made his decision. He eased the throttles back slightly, letting airspeed bleed from 180 down to 160, then 150, then 140. The descent rate decreased from 300 feet per minute to 250, then 200. Every foot of altitude lost now covered more horizontal distance. The glide ratio was improving, extending their range, but they were still nowhere close to making the Belgian coast. The mathematics remained unforgiving. Even at optimal glide speed with partial power, Jeannie Marie was going down over Germany. The only question was where. Rentmeester glanced at his fuel gauges. The bomber had launched with 2,800 gallons of aviation gasoline distributed across tanks in the wings and fuselage. Combat operations plus the flight to target had consumed approximately 2/3 of that fuel. Roughly 900 gallons remained. At current fuel consumption rates with 3 engines operating, Rentmeester estimated he had fuel for another 90 minutes of flight. 90 minutes. That timeline exceeded his altitude budget. He'd hit the ground in 70 minutes at current descent rate, which meant fuel wasn't the limiting factor. Altitude was the currency he was trading for distance, and he was running out of altitude faster than he could convert it into miles covered. The crew worked silently, each man at his station, monitoring for German fighters, watching instruments, praying in whatever fashion made sense to them. Sergeant Rudy Malkin in the radio room monitored the command frequencies, listening for any traffic that might indicate fighters being vectored toward their position. The waist gunners, Sergeant Ward Simonson and Sergeant Gordon Wiggett, scanned the sky through their gun positions, looking for the silhouettes that meant death was approaching at 300 miles per hour. Minutes passed, then 10 minutes, then 20. Jeannie Marie descended through 18,000 feet, still heading west, still burning altitude like water draining from a punctured tank. Every 1,000 feet of altitude lost brought them closer to the certainty of a crash landing somewhere in occupied Europe. Then something changed. Something Rentmeester hadn't expected. Something that transformed his desperate calculation from impossible to merely improbable. They hit a weather system moving from west to east, a frontal boundary, where warmer air from the Atlantic collided with colder continental air over northern Europe. The boundary created lift, rising air currents that could carry a glider upward without any power whatsoever. Sailplane pilots called these thermals when they formed over land heated by the sun, or wave lift when they formed in mountainous terrain. Here, in the winter sky over Germany, it was simple frontal lift from a weather system moving through the region. Rentmeester felt it first in the controls. The aircraft suddenly stopped descending. The variometer, the instrument that showed rate of climb or descent, swung from 200 feet per minute down to 0, then briefly indicated a climb. The bomber was flying through rising air that exactly counterbalanced its natural tendency to descend. The lift didn't last long. Maybe 3 minutes. Maybe 5. Then they were through it, back to descending at 200 feet per minute. But those few minutes of 0 descent rate translated into distance covered without losing altitude. The mathematics shifted in their favor, imperceptibly but meaningfully. They passed through 15,000 feet at 12:15 hours, approximately 55 minutes into their emergency return flight. Rentmeester checked his navigation. Lieutenant Roberts confirmed they'd covered approximately 130 miles from the point where they'd left the formation, 220 miles remaining to the Belgian coast. 15,000 feet of altitude remaining. Still not enough, but closer. Then engine number 3 quit. No warning, no gradual degradation. The engine simply stopped producing power. Cylinder head temperature had climbed past red line limits. Something internal had failed. Piston, connecting rod, valve assembly, something, and the engine was no longer capable of generating thrust. Behrend immediately hit the feathering button for engine number 3. This time the feathering motor worked. The propeller blades rotated to their feathered position, reducing drag. But now Jeannie Marie was flying on 2 engines, number 1 and number 4, both outboard engines, both operating at war emergency power that was slowly destroying them. Descent rate increased to 300 feet per minute. The aircraft slowed despite Rentmeester's attempts to maintain airspeed. Glide ratio degraded. The mathematics turned against them again. They were going to hit the ground somewhere in western Germany. That certainty crystallized in Rentmeester's mind with cold clarity. The question became whether they could make it far enough west to reach territory recently liberated by Allied forces, or whether they'd crash in occupied territory where the crew would face capture or death. They descended through 12,000 feet, then 10,000, then 8,000. The ground rose to meet them. Through breaks in the lower cloud deck, Rentmeester could see German countryside, fields, forests, villages, roads. No obvious landing sites, no friendly forces visible, just enemy territory extending to every horizon. At 5,000 feet, approximately 100 miles from the Belgian coast, Rentmeester began looking for emergency landing options. A field large enough for a B-17. Flat terrain without obstacles. Something that wouldn't kill them all instantly when the bomber hit the ground at 140 miles per hour. Then, against all odds, against all probability, they caught another band of frontal lift, rising air that arrested their descent, that bought them precious minutes, that extended their glide just a little bit further west, just a little bit closer to friendly territory. 3,000 feet, 2,000, 1,000. The altimeter unwound with terrifying speed. They were flying barely above the treetops now, engines screaming at war, emergency power, airframe shaking, men praying. Rentmeester saw the border. He didn't know exactly where the front lines were, but he saw terrain that looked less organized, less orderly, the devastation of recent combat operations, shattered buildings, cratered fields, the unmistakable signature of ground warfare. And then, impossibly, wonderfully, he saw an airfield, Allied markings on the control tower, fighters parked on hard stands, an emergency landing strip large enough for a B-17. He had no radio. The electrical system was damaged. He couldn't communicate with the tower. He simply lined up on the runway and committed to landing. Either the tower would clear him, or they wouldn't. Either way, he was out of options. Jeannie Marie touched down hard, bounced once, settled onto the runway, and rolled to a stop. When Rentmeester finally shut down the 2 remaining engines, they'd been operating continuously at war emergency power for 100.3 minutes. Post-flight examination of the engines showed they were minutes away from catastrophic failure, bearing temps beyond safe limits. Cylinder, heads cracked from thermal stress, connecting rods stretched from sustained high-load operation. The engines had given everything they had, and it had been exactly enough. The bomber had covered approximately 260 miles from the point where they'd left the formation over Oschersleben to the emergency landing in Belgium. They'd descended from 24,500 feet to ground level, trading every foot of altitude for distance, stretching the glide through a combination of skill, luck, weather systems, and the remarkable engineering of a machine designed to bring its crew home against impossible odds. All 10 crew members walked away from the aircraft. Sergeant Hugh Eckenrode, the tail gunner, counted over 200 holes in the fuselage from cannon shells and machine gun rounds. The number 2 engine was unsalvageable. The number 3 engine was destroyed. Engines 1 and 4 would require complete overhauls before they could fly again. Jeannie Marie never returned to combat operations. The bomber was stripped for parts and scrapped, but her crew survived. They'd completed their mission not by bombing the target, but by demonstrating what a B-17 could do when pushed beyond its operational limits by a pilot who understood that altitude wasn't just vertical distance. It was a currency that could be traded for horizontal distance, if you knew the exchange rate and were willing to accept the risks. The Army Air Force's tactical manual for B-17 operations included a table showing glide performance. Distance covered versus altitude available. The manual stated that a B-17 without power could glide approximately 16 feet forward for every 1 foot of altitude lost. This translated to roughly 70 to 80 miles of glide range from 25,000 feet. Captain Rentmeester had just extended that range to over 260 miles by using partial power, optimal airspeed, weather systems, and every bit of skill he'd accumulated in 7 years of flying. The manual didn't have a table for that scenario. Nobody had calculated those numbers because nobody expected pilots to push aircraft so far beyond normal parameters and survive. The concept of stretching a glide wasn't theoretical when Rentmeester executed his emergency return on February 22, 1944. Every pilot who flew multi-engine aircraft understood the basic principle. Altitude could be traded for distance. But understanding a principle academically and executing it under combat conditions with damaged engines, battle damage affecting aerodynamics, and the psychological pressure of knowing that 10 lives depended on your calculations were entirely different matters. The B-17 Flying Fortress had been designed from its inception to operate at altitudes where most fighters struggled to maintain performance. The turbo-supercharged Wright Cyclone, R. 1,820 engines, maintained sea-level power output up to approximately 25,000 feet. This altitude advantage was supposed to keep the bombers above the worst of German anti-aircraft fire and provide an advantage against intercepting fighters. But altitude advantage created its own paradox. Operating at 25,000 feet meant exposure to atmospheric conditions that human bodies weren't designed to tolerate. Outside air temperature at that altitude averaged -60 degrees Fahrenheit in winter. The partial pressure of oxygen was insufficient to support consciousness without supplemental oxygen systems. Equipment froze. Hydraulic fluid thickened, metal contracted, creating stress points that could fail under load. The B-17's pressurization system was rudimentary by later standards. The aircraft wasn't pressure-sealed like post-war airliners. Crew members wore oxygen masks continuously above 10,000 feet. Heated flight suits provided protection against cold, though the heating systems frequently malfunctioned, leaving gunners with frostbitten fingers and toes after 8-hour missions. But that altitude, that precious altitude measured in thousands of feet, represented survival margin when engines failed or battle damage reduced aircraft performance. Every 1,000 feet of altitude above terrain was potential energy that could be converted into kinetic energy. Forward motion. The conversion wasn't perfectly efficient. Drag consumed energy. But a skilled pilot could maximize efficiency, extracting the maximum distance from available altitude. The aerodynamics governing glide performance were well understood by 1944. The Wright brothers had studied glide ratios during their early experiments at Kitty Hawk. German engineers working with sailplanes during the 1930s had refined the mathematics. Every aviation engineering textbook included chapters on unpowered flight characteristics. A glide ratio of 16:1 meant that for every 16 feet traveled horizontally, the aircraft descended 1 foot vertically. This ratio depended on the aircraft's lift-to-drag ratio. The relationship between the lifting force generated by the wings and the total drag opposing forward motion. The B-17, designed for high-altitude operation and heavy defensive armament, wasn't optimized for glide performance. Its drag coefficient was relatively high compared to sailplanes or even lighter aircraft, but 16:1 was the baseline with engines at idle and propellers windmilling. The ratio improved significantly when pilots could feather propellers, reducing drag. It improved further when pilots maintained optimal glide speed, minimizing total drag. And it improved dramatically when pilots could extract even partial power from damaged engines, supplementing glide performance with thrust. The skill lay in finding the optimal balance. Too much power meant burning through limited fuel reserves without proportional improvement in range. Too little power meant accepting a steeper glide angle and shorter range. The perfect balance maximized distance covered per unit of fuel consumed while maintaining sufficient airspeed for control authority. Rentmeester had found that balance through intuition, experience, and constant recalculation as conditions changed. When engine number 3 failed, he'd instantly adjusted airspeed and power settings on the remaining 2 engines to compensate. When they'd encountered lifting air currents, he'd recognized the opportunity and used the lift to cover distance without losing altitude. Every decision extended their range incrementally. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The broader context of these emergency situations was the strategic bombing campaign itself. By February of 1944, the 8th Air Force had been conducting daylight precision bombing raids against German industrial targets for 18 months. The campaign had cost thousands of lives and hundreds of aircraft. Results were mixed, at best. Precision bombing doctrine assumed that attacking specific industrial targets would cripple Germany's war-making capacity more efficiently than the British strategy of nighttime area bombing. American bombardiers used the Norden bombsight, a sophisticated analog computer that calculated bomb trajectories based on altitude, airspeed, wind conditions, and target motion. In theory, the Norden bombsight could place bombs within a 100-foot circle from 25,000 feet. In practice, weather, battle damage, fighter attacks, and the simple chaos of combat operations degraded accuracy substantially. Post-strike reconnaissance photographs showed that many bombing raids missed their intended targets entirely. Bombs that were supposed to hit aircraft factories destroyed residential neighborhoods. Raids targeting ball-bearing plants caused minimal disruption to German production because redundant manufacturing capacity absorbed the damage. The human cost was staggering. 8th Air Force bomber crews faced casualty rates comparable to infantry units fighting in the most intense ground campaigns. During the darkest months of 1943, before long-range escort fighters became available, bomber losses exceeded 20% on some missions. 1 aircraft in 5 failed to return. Statistically, flying 25 missions meant rolling dice with death 5 times, knowing that each roll carried a 20% chance of catastrophic loss. The bombers themselves became flying coffins for many crews. A B-17 struck by anti-aircraft fire could explode instantly if fragments penetrated fuel tanks or bomb bays loaded with ordnance. Fighter attacks with 20mm cannons and 13mm machine guns could shred aluminum skin, sever control cables, kill crew members, and set engines ablaze. Fires at altitude were particularly terrifying because crew members had minutes to bail out before flames consumed the aircraft or structural failure caused breakup. Parachuting from a damaged bomber over enemy territory meant capture if the crewman survived the landing. German civilians, enraged by years of bombing raids that destroyed their cities, sometimes killed downed airmen before military authorities could intervene. Luftwaffe pilots occasionally machine-gunned parachuting crewmen, though standing orders from senior commanders prohibited such actions. Captured airmen faced interrogation at Dulag Luft near Frankfurt, then transport to prisoner-of-war camps where they'd spend the remainder of the war. The alternative, staying with a damaged aircraft and attempting to reach friendly territory, was often more dangerous than bailing out. But it meant the possibility of returning to base, of surviving to fly again, of not becoming a prisoner. This calculation shaped countless emergency decisions by pilots facing impossible situations. Captain Rentmeester's decision to stay with Jeannie Marie and attempt the emergency flight back to friendly territory reflected this calculation. Bailing out over Germany meant capture for the entire crew. Staying with the aircraft meant risking a crash landing, but with the possibility of making it far enough west to reach Allied lines. The mathematics favoured attempting the flight as long as the aircraft remained controllable. Other B-17 crews faced similar decisions during missions throughout 1944. The patterns repeated across hundreds of individual incidents: battle damage reducing engine power, crews jettisoning weight to extend range, pilots calculating glide ratios and fuel consumption, desperate attempts to reach the English Channel or Allied-held territory before running out of altitude or fuel. On December 20, 1943, Second Lieutenant Charles Brown piloted the B-17 Ye Old Pub back from a raid on Bremen, Germany. Fighter attacks had killed his tail gunner, wounded several other crew members, destroyed 2 engines, and left a 3rd engine operating at half power. Brown flew the crippled bomber across Germany and the North Sea with minimal power, landing at an emergency airfield on the English coast. The bomber had sustained damage that made continued flight seem impossible, yet Brown had brought it home through a combination of skill and the B-17's legendary structural resilience. On February 1, 1943, Lieutenant Kendrick Bragg piloted the B-17 All-American after a mid-air collision with a German fighter over Tunisia. The collision nearly severed the bomber's fuselage aft of the wings. The tail section remained attached by a single elevator control cable and some structural stringers. The bomber was essentially broken in half, yet Bragg maintained control, flew 90 miles back to base, and executed a successful emergency landing. The aircraft collapsed into wreckage after the crew evacuated, but all crew members survived. On February 22, 1944, the same day Rentmeester was fighting to keep Jeannie Marie airborne over Germany, dozens of other B-17 crews faced similar emergencies. Multiple aircraft from the same raid returned with severe battle damage. Some made it home, some crashed attempting emergency landings, some went down over enemy territory. The individual stories blurred together into a statistical pattern. Some crews survived impossible situations through skill and luck, others didn't. The engineering that made these survivals possible reflected design choices made years earlier when Boeing engineers drafted the initial specifications for the Model 299 prototype. The B-17's structure emphasized strength and redundancy. The fuselage incorporated multiple load-bearing frames and stringers. Control cables were duplicated so that battle damage cutting one cable didn't eliminate control authority. Fuel tanks were self-sealing, incorporating rubber layers that swelled when exposed to aviation, gasoline, plugging bullet holes, and preventing catastrophic leaks. The engines themselves were designed for reliability rather than maximum power output. The Wright R-1820 Cyclone was a 9-cylinder radial engine producing 1,200 horsepower at normal ratings. It was air-cooled, eliminating the vulnerability of liquid-cooled engines that could fail catastrophically when coolant lines were damaged. The radial configuration provided inherent balance and distributed power loads across multiple cylinders, allowing the engine to continue operating even when several cylinders failed. But the engines had limits. Operating continuously at war emergency power, 51 inches of manifold pressure and 2,250 RPM, generated cylinder head temperatures and bearing loads that exceeded design specifications. Engine manufacturers rated war emergency power for 5-minute maximum duration, specifically because sustained operation at these settings caused accelerated wear and risked catastrophic failure. Rentmeester had operated his remaining engines at war emergency power for over 100 minutes. Post-flight inspection revealed the damage. Piston rings were worn beyond serviceable limits. Cylinder head cracks radiated from spark plug holes. Main bearing clearances had opened up as metal expanded under sustained thermal loading. Oil analysis showed metal particles indicating advanced wear. The engines had been destroyed incrementally, trading their mechanical life for thrust that kept the bomber airborne. This trade-off, sacrificing equipment to save lives, pervaded combat operations. Aircraft were expensive. A B-17G in 1944 cost approximately $238,000, equivalent to roughly $4 million in modern currency. But aircraft could be replaced. Trained crews couldn't, at least not quickly. Training a bomber, crew from recruitment through combat-ready status required approximately 1 year and cost far more than the aircraft itself when training expenses, instructor time, and infrastructure were calculated. The Army Air Forces explicitly prioritized crew survival over aircraft preservation. Technical orders and training manuals instructed pilots to use any means necessary to bring damaged aircraft back to friendly territory, even if those methods would destroy the engines or airframe. Better to land a wrecked aircraft that could be scrapped than to lose a trained crew that would require a year to replace. This calculation shaped maintenance and operational procedures. Mechanics understood that combat-damaged engines would often require complete overhaul or replacement, even if they appeared serviceable. Pilots knew that pushing engines beyond limits during emergencies was not just permitted, but expected. The culture accepted aircraft as expendable tools rather than precious resources to be preserved. The broader industrial context supported this philosophy. American aircraft production in 1944 approached 5,000 B-17 seconds annually. Boeing's Seattle plant, the Douglas facility at Long Beach, and the Lockheed Vega plant at Burbank produced flying fortresses in quantities that German industry couldn't match. Losses that would have been crippling for the Luftwaffe were sustainable for American forces simply because replacement aircraft arrived continuously. But crew replacement couldn't scale as easily. Training new pilots required flight instructors who were themselves experienced aviators. Training new bombardiers required time on the Norden bomb site, which was classified equipment available only at secure facilities. Training new navigators required extensive classroom instruction in celestial navigation, dead reckoning, and radio navigation techniques. The entire training pipeline took months and consumed resources that couldn't be rapidly expanded. So, when Captain Rentmeester pushed his engines past sustainable limits to bring his crew home, he was executing doctrine. He was following implicit guidance that valued crew survival over equipment preservation. The fact that Jeannie Marie was scrapped afterward was irrelevant. The 10 crew members who walked away would fly again, accumulating experience that made them more valuable with every mission survived. The psychological dimension of these emergency situations deserves examination. Modern research into pilot decision-making under stress reveals patterns that help explain how aviators like Rentmeester managed extreme situations. High-stress emergency conditions activate physiological responses that can either enhance or degrade performance, depending on the individual and the specific circumstances. Adrenaline release increases heart rate, sharpens sensory perception, and improves reaction time. But excessive stress triggers tunnel vision, impairs complex reasoning, and degrades working memory. The difference between effective emergency response and panic-induced catastrophic decisions often comes down to training and experience that help pilots maintain cognitive function when their bodies are screaming danger signals. Rentmeester's experience: 7 years of flying, over 2,000 hours, 23 previous combat missions, provided mental patterns that helped him process the emergency systematically rather than reactively. When his number 2 engine failed, he didn't panic. He executed, memorized emergency procedures, reduce power, attempt to feather the propeller, assess remaining capability, decide on course of action. Each step followed logically from training that had been repeated until it became automatic. The continuous recalculation of glide range, fuel consumption, and optimal airspeed required conscious cognitive effort, but it was effort applied within a framework of practiced procedures. Rentmeester wasn't inventing solutions in real time. He was selecting from a menu of options he'd rehearsed mentally during training flights and previous missions. The specific circumstance was novel, but the components were familiar. His crew's response similarly reflected training and experience. Each man remained at his station, performing assigned duties without being told. The navigator calculated headings. The flight engineer monitored remaining engine performance. The gunners watched for fighter attacks. Radio operator attempted to establish communications. Nobody panicked. Nobody made the situation worse through ill-considered actions. This crew coordination was itself a product of doctrine and training. B-17 crews trained together as units rather than as individuals who would be assembled into crews later. This fostered trust and mutual understanding. Each crew member knew what the others would do in specific situations. Communication could be minimal, because shared mental models meant everyone understood the situation and appropriate responses. The contrast with German bomber crews is illuminating. Luftwaffe doctrine emphasized individual skill and initiative. German pilots were often exceptional aviators, but their crews were sometimes assembled ad hoc from available personnel. This reduced crew coordination and created situations where miscommunication or misunderstanding could cascade into disasters. American doctrine accepted that individual aircrew members might be less skilled than their German counterparts, but compensated through superior crew coordination, better training standardization, and emphasis on procedure-based decision-making. The result was generally comparable performance, with better outcomes in emergency situations where coordination mattered more than individual virtuosity. The specific emergency Rentmeester faced, multiple engine failures with insufficient power to maintain altitude, had occurred before and would occur again. The Army Air Forces had accumulated substantial data on B-17 performance with engine failures. Technical reports documented that a fully loaded B-17 could not maintain altitude on 2 engines. 3 engines provided minimal capability. 4 engines were necessary for sustained flight at combat altitudes with full payload. But these reports assumed normal flight conditions: level flight or shallow climbs, standard power settings, good weather. Emergency conditions allowed, sometimes required, violating normal parameters. War emergency power provided thrust unavailable in peacetime operations. Jettisoning bombs and equipment reduced weight beyond normal mission planning. Optimal glide speeds extracted maximum range from available altitude. The reports also didn't account for weather phenomena that could dramatically extend range. Frontal lift, the rising air currents where different air masses collided, could reduce or eliminate descent rate temporarily. Wave lift from air flowing over terrain features could provide similar benefits. Skilled pilots who understood meteorology could sometimes exploit these conditions to extend range beyond what pure aerodynamics suggested possible. Rentmeester's encounter with frontal lift twice during his emergency return wasn't entirely coincidental. Weather briefings before the mission had indicated a frontal system moving across northern Europe. Rentmeester knew the system was there and consciously maneuvered to remain within lifting air as long as possible. This wasn't luck. It was knowledge applied deliberately to solve an immediate problem. The distinction between luck and skill in survival stories is often unclear. Rentmeester was lucky that his remaining engines didn't fail completely. He was lucky that German fighters didn't press attacks on a clearly crippled bomber. He was lucky that the emergency airfield appeared when and where it did. But he created opportunities for luck to matter by maintaining control, by flying optimal profiles, by making thousands of micro-decisions that individually seemed insignificant but collectively determined whether the bomber would cover sufficient distance to reach friendly territory. The aftermath of missions like this one extended beyond immediate survival. Rentmeester and his crew were debriefed extensively. Intelligence officers wanted to understand exactly what had happened, where they'd been hit, what damage they'd sustained, how they'd managed the return flight. This information fed into tactical analyses that shaped future mission planning. The technical debrief focused on aircraft performance and failure modes. Engineering officers examined the damaged engines to understand what had failed and why. This data influenced maintenance procedures, operational limits, and design modifications for future aircraft. Every emergency contributed to accumulated knowledge that improved survival rates incrementally. Rentmeester himself flew again after Jeannie Marie was scrapped. He completed his 25-mission combat tour and returned to the United States. Like most combat aviators, he rarely discussed his experiences afterward. The psychological burden of sustained combat operations affected most crew members to varying degrees. Some adapted well to post-war civilian life. Others struggled with what would later be termed post-traumatic stress disorder, though the condition wasn't formally recognized in 1944. The crew of Jeannie Marie scattered after the war. Some remained in aviation, leveraging their military experience into civilian flying careers. Others returned to farms, factories, and offices, putting the war behind them as thoroughly as possible. Sergeant Elmer Dythorn, the flight engineer, lived until 1998 and occasionally spoke at veterans' events about his experiences. Lieutenant Bob Roberts, the navigator, wrote a brief memoir that remains in family archives, but was never published. The bomber itself disappeared into the vast machinery of wartime logistics. Stripped for parts at a repair depot somewhere in England or Belgium, its components were probably cannibalized to repair other damaged aircraft. The fuselage was likely smelted down for aluminum to be reused in new production. Nothing physical remained of Jeannie Marie by 1945, but the story persisted, at least within the 91st Bombardment Group. Rentmeester's emergency return became one of those missions that newer crews heard about during informal briefings. The details shifted slightly with each retelling, as such stories always do, but the core remained. A crippled bomber, impossible odds, a crew brought home through skill and determination. Similar stories accumulated throughout the 8th Air Force. The B-17, Memphis Belle, which completed 25 missions and returned to the United States for a publicity tour, became famous partially because of several instances where battle damage should have been fatal, but the two aircraft survived. The bomber 909 completed 140 missions, accumulating damage and repairs that would have destroyed lesser aircraft. These stories reinforced the B-17's reputation for toughness and survivability. The reputation mattered psychologically. Crews boarding aircraft for missions faced terrifying odds. Knowing they flew bombers with a track record of bringing damaged aircraft home provided psychological comfort, even if the comfort was partially illusory. Aircraft survived because of design characteristics, but also because of crew actions, maintenance quality, and pure chance. Attributing survival to the aircraft itself simplified a complex causal chain into something easier to grasp. The engineering community learned systematic lessons from these emergency situations. Post-war aircraft design incorporated features derived from wartime experience. Redundant control systems became standard. Engine placement evolved to provide better single-engine or engine-out performance. Glide ratios improved as designers optimized aerodynamics. The B-17's legacy influenced aircraft design for decades afterward. But the human lessons were harder to codify. How do you train pilots to make optimal decisions under extreme stress, when variables shift continuously and perfect information is never available? How do you develop the judgment that distinguishes between aggressive risk-taking that saves lives and reckless risk-taking that kills everyone aboard? The Army Air Forces tried. Training programs emphasized emergency procedures, decision-making under stress, and crew coordination. Simulator technology was primitive in 1944, but instructors used whatever tools available to create realistic emergency scenarios. The goal was developing mental patterns that would activate automatically when real emergencies occurred. The success rate was imperfect but meaningful. Not every crew survived emergency situations. Not every pilot made optimal decisions. But enough crews survived, and enough pilots made good decisions, that the strategic bombing campaign continued despite horrific losses. The mathematical calculus was brutal. If crew survival rates exceeded replacement rates, the campaign could continue. If survival rates fell below replacement rates, the campaign would collapse, as experienced crews were attrited faster than new crews could be trained. By February of 1944, the calculus was shifting in favor of the Allies. Long-range escort fighters, primarily the P-51 Mustang, were becoming available in sufficient numbers to provide protection throughout missions. Fighter escorts reduced bomber losses from 20% on some missions to 5% or less. This dramatic improvement meant that crews had reasonable chances of completing their 25-mission tours. But individual missions still generated situations like Rentmeester's emergency return. Battle damage still caused engine failures. Anti-aircraft fire still shredded bombers. The difference was that more crews survived because losses overall were declining and because accumulated experience improved emergency procedures. The specific tactical lessons from extended emergency glides influenced future operations. Briefing officers emphasized maintaining maximum practical altitude over enemy territory. The extra 1,000 or 2,000 feet might seem insignificant during normal operations, but it provided crucial margin when engines failed. Pilots were explicitly instructed to trade airspeed for altitude when circumstances permitted, banking altitude that could be converted to distance during emergencies. Navigation procedures evolved to account for emergency situations. Navigators plotted not just the direct route to and from targets, but also emergency routes to Allied airfields, neutral countries, or coastline. These alternate routes provided options when primary routes became unfeasible. Knowing where you were relative to friendly territory at any moment made emergency decisions clearer. Fuel management became more sophisticated. Standard procedure was to use fuel from fuselage tanks first, then wing tanks, leaving fuel distributed in ways that maintained balance as consumption proceeded. But emergency procedures sometimes called for deliberately unbalancing fuel loads to optimize single-engine or reduced-power flight characteristics. Pilots learned these nuances through training and experience. The remarkable aspect of Rentmeester's emergency return wasn't any single element. Multiple B-17 crews faced similar situations. Many succeeded in reaching friendly territory. What makes the specific incident historically significant is how clearly it illustrated principles that governed countless other emergencies. Altitude as currency, optimal glide speeds, weather exploitation, crew coordination, and the simple determination to keep fighting for survival until the last possible moment. The bomber's glide ratio of 16:1 meant that every decision affecting drag or lift had proportional effects on range. Feathering one propeller, instead of letting it windmill, might extend range by 5 miles. Maintaining optimal airspeed might add 10 miles. Jettisoning unnecessary weight might add another 5 miles. Individually, these margins seemed insignificant. Collectively, they determined whether the crew bailed out over Germany or landed in friendly territory. This incrementalism, the understanding that small improvements compound into meaningful differences, characterized successful emergency responses throughout the air war. Pilots who survived impossible situations rarely did so through single dramatic actions. They survived through continuous sequences of small decisions that individually seemed trivial but collectively determined outcomes. The mathematical precision required for these calculations was remarkable given the circumstances. Rentmeester was calculating glide ratios, fuel consumption rates, and distance to friendly territory while sitting in a vibrating aircraft, in extreme cold, wearing oxygen masks that made communication difficult, with battle damage affecting instruments, while scanning for German fighters that could appear at any moment. The cognitive load was enormous, yet he maintained situational awareness and made decisions that proved correct. Modern cockpit resource management training emphasizes distributing cognitive load across crew members to prevent overwhelming any individual. The pilot flying concentrates on aircraft control. The pilot not flying manages systems and communications. Other crew members handle navigation, weapons, defensive systems. This distribution prevents the cognitive overload that causes errors. 1944 B-17 operations used similar principles, though not formalized into explicit cockpit resource management doctrine. Rentmeester focused primarily on flying the aircraft, while his co-pilot managed throttles and systems. The navigator calculated headings and distances. The flight engineer monitored remaining engine performance. Each crew member contributed to the overall solution without requiring detailed coordination at every step. The trust required for this distribution of responsibility was substantial. Rentmeester had to trust that his navigator's calculations were correct, that his flight engineer would alert him to critical engine problems, that his co-pilot would manage systems appropriately. Any failure in this trust chain could have cascaded into disaster. The fact that the system worked reflected training, shared understanding, and the bonds formed through previous missions together. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.